In this video, we will work through some multiple choice questions from previous AP Calculus exams which pertain to Unit 3. For problem number 1, we are given the equation for f double prime, the second derivative, and we are being asked where the original function f will have inflection points. We know that the original function f of x will have a point of inflection wherever f double prime changes signs. So let's start off by finding where f double prime is equal to 0, and then we will use those values to make a sign chart and find out where the sign changes. So because this is already in factored form, we can just look at each factor and tell that the solutions will be x equals 0 from that first factor, and then x equals -1 from the middle factor, and x is equal to +2 from the last factor. So let's put these three numbers on a number line and make a sign chart. So here I've put the three values on the number line. Make sure you label the sign chart as f double prime, and then you need a row for each of the factors that you have. Let's decide whether each factor is positive or negative in each interval. So starting with x, x itself will be negative for values that are less than 0, obviously. So x will be negative here, and x will be positive here and here. Now, if you set x plus 1 equal to 0, that's what gave us the value of -1. So for x values less than -1, x plus 1 will be negative. For x values that are greater than -1, x plus 1 will be positive. So x plus 1 will be positive here and here and here. This last factor will always be positive. Can you guess why? It's being squared. So if you square something, it's always going to be positive. Now let's consider the overall sign of f double prime. And I'm really just focusing on the negatives. If I have an even number of negatives, then that's going to be a positive. If I have an odd number of negatives, that's going to be a negative. If I have nothing but positives, that's going to be positive. So we are looking for where f double prime changes signs. So we're going from positive to negative. So we have a sign change at -1. We are going from negative to positive. So we have a sign change at 0. And there is no sign change there's no sign change at 2, because you're just going from positive to positive. If this were a free response question, this is how I would summarize and justify my answer. F of x has a point of inflection at x equals -1 and x equals 0 because f double prime changes signs. But this was a multiple choice question, so we can see that the answer is C. By the way, a point of inflection is where a function changes concavity. So for example, in this picture, the left side of the function is concave up, and then at this point, it changes to being concave down. So that's what makes this a point of inflection. And the reason why we are using the second derivative is because we have learned that if the second derivative is positive, that means that the original function is concave up. If the second derivative is negative, then the function is concave down. So therefore, if the second derivative changes signs, for example, if the second derivative goes from positive to negative, then that means the concavity went from concave up to concave down, which would give you a point of inflection. Just wanted to make sure you understood what's going on behind the scenes. Number 2, for what value of k will x plus k over x have a relative maximum at x equals negative 2? Let's call this f of x. However, let's rewrite it ever so slightly as x plus k times x to the negative 1 power, just moving this x in the denominator on up. A function can only have a relative maximum when the first derivative is either equal to 0 or undefined. So we need to find the first derivative and check it out. The derivative of x is 1. And then using the power rule, I'm going to multiply negative 1 times k and make this negative k. And reducing this power by 1 gives me negative 2. I've seen into the future, and I know we will ultimately need the second derivative test. So I'm going to go ahead and find the second derivative right now. So the derivative of 1 is 0. And using the power rule, negative 2 times negative 1 is positive 2. So we will have positive 2k. And reducing this power by 1 gives us the negative third power. Rewriting f prime so that we don't have a negative exponent, we have f prime is equal to 1 minus k over x squared. We know that a relative maximum or a relative minimum can only occur if the first derivative is either equal to 0 or is undefined. Let's get the undefined part out of the way first. F prime will only be undefined if this denominator is 0. In other words, if x is equal to 0. But we are only being asked to find the values of k that will cause a relative maximum at x equals negative 2. So we don't care what's happening at x equals 0, so we can forget about this part. So let's consider the values of k that will cause the first derivative to equal 0. Let's start by setting the first derivative equal to 0. So we have 1 minus k over x squared equals 0. Let's add k over x squared to both sides. So that gives us 1 is equal to k over x squared. We want to find the value of k that will cause a relative maximum at x equals negative 2. So we are only interested in an x value of negative 2. So let's go ahead and substitute negative 2 in and see what that tells us. So we have 1 is equal to k over negative 2 squared. So that's 1 is equal to k over 4. Multiplying both sides by 4, we get k is equal to 4. So we now know that 4 is the only value of k that will cause the first derivative to equal 0 at x equals negative 2. So we can forget about option A, B, and C. But we don't know for sure that D is the right answer. It still could be none of these. The fact that the first derivative is equal to 0 only tells us that we have a horizontal tangent line at x equals negative 2. But there are 3 different ways that you could have a horizontal tangent line. If the function is concave up at x equals negative 2, then the point of tangency is a relative minimum. If the function is concave down, then it is a relative maximum. And if the function is neither concave up nor concave down, we have a point of inflection. In all 3 cases, f prime is equal to 0. So how can we tell which one we have? The answer is we can use the second derivative test. We have learned that the function will be concave up if the second derivative is positive, and concave down if the second derivative is negative. Rewriting the second derivative to get rid of the negative exponent, we have f double prime equals 2k over x to the third power. If k is equal to 4, then we have 2 times 4 over x to the third power, and f double prime is 8 over x to the third power. We need to see what happens at x equals negative 2. So f double prime at negative 2 would be 8 over negative 2 cubed. Remember that cubing a negative number does not make the negative sign go away. So we end up with 8 over negative 8, which equals negative 1. So what really matters here is that the second derivative at negative 2 is negative. So that means we are in the situation where the function is concave down, which means that the point of tangency will be a relative max. That is exactly what we were shooting for, so the answer is D. By the way, if this had been a free response question, this is how we would have summarized and justified our answer. F of x has a relative max at x equals negative 2 when k equals 4 because f prime at negative 2 is equal to 0 and f double prime at negative 2 is negative. Notice that if you want to use the second derivative test to justify a relative max, you actually need both of these facts. F prime equals 0 guarantees that we have a horizontal tangent line. F double prime being negative tells us that the function is concave down, which makes it a relative max. If we wanted to justify a relative min, we would show that f double prime is positive. The graphs of the derivatives of the functions f, g, and h are shown above. So these are the derivatives of the original functions. Which of the functions f, g, and h have a relative maximum on the open interval from a to b? So just to be very clear, these are not the original functions. So we're not just looking and going, oh, there's a relative max here and here. No, these are the derivative functions, but we are being asked whether the original functions have a relative maximum on the interval. So for there to be a relative maximum, two things need to happen. The first thing is that the derivative has to equal 0. If the derivative equals 0, that means the slope is equal to 0, which means we have a horizontal tangent line. But a horizontal tangent line can occur in two ways, 3 if you count a point of inflection. But a horizontal tangent line could be at a relative max or a relative min. But this is still a good place to start. Let's look for all of the places on these graphs where the derivative is equal to 0. So we're looking for where these graphs touch the x-axis. Since these are the derivatives, f prime is equal to 0 here, here, and here. So for this graph, these are the only possible candidates for the location of a relative maximum. For the graph of function g, this is the only candidate for a local maximum. For function h, the derivative h prime is never 0. So h prime does not have any relative maximum on the interval from a to b. So how can we tell if these points are the location of a relative maximum? Well, if this point of tangency is a relative maximum, then the function is increasing on the left and then decreasing on the right. Remember the graphical relationship between f and f prime. If the function is increasing, then f prime should be positive. If the function is decreasing, f prime should be negative. So for a relative maximum, the function goes from increasing to decreasing. That means that f prime should go from positive to negative. So we need to analyze each of these points and see if f prime or g prime goes from positive to negative at the point that we are analyzing. So for this first point, f prime goes from negative, because it's below the x-axis, to negative again. So it goes from negative to negative. So we know this is not the location of a relative maximum. For the next point, it goes from negative to positive. All right, so that would be the location of a relative minimum, because decreasing to increasing. So not a relative maximum. The third point is above the x-axis and then below the x-axis. So it goes from positive to negative. So guess what? This is the location of a relative maximum. All right, now how about the next one? Well, this last one again goes from negative to positive. So this would be a relative minimum with a decreasing and then increasing. So only function f has a relative maximum on the interval from a to b. So that means the answer is A. If the position of a particle on the x-axis at time t is negative 5t squared, then the average velocity of the particle for the interval from 0 to 3 is which of these? So we are given this position function, and we know that velocity is the change in position divided by the change in time. If we were being asked for the instantaneous velocity, in other words, if we were being asked for the velocity at a specific moment in time, then we would use the derivative. And that would be negative 10t. And then we could use that formula to find the instantaneous velocity at any time t. But they did not ask us to find the instantaneous velocity. They're asking for the average velocity. Remember back in Algebra 1, when you found the slope by finding y2 minus y1 over x2 minus x1. If they ask you for the average velocity, then this is what you are really going to do. So let's see, average velocity. Okay, let's actually start with the x2 minus x1. These values will come from the interval itself. So the x2 is the 3, and the x1 is the 0. We know that the value of a function is the y value. So our y2 minus y1 will be the position at 3 minus the position at 0. So evaluating our position function at 3 and 0, we get this expression minus this expression. Of course, 5 times 0 squared is 0, so this part of the function is gone, and this is just 0. So let's simplify this down. We have in the denominator just 3. 3 squared is 9. 9 times 5 is 45. So we have negative 45. And negative 45 divided by 3 is negative 15. So the answer is C. Number 5, a particle moves along the x-axis so that at any time t greater than or equal to 0, its position is given by this function. For what values of t is the particle at rest? At rest implies that the velocity is equal to 0. And we know that the velocity is the derivative of the position function. So the derivative must equal 0. So let's take the derivative of the position function and set it equal to 0. That will be 3t squared minus 6t minus 9. And that's going to equal 0. Dividing both sides of the equation by 3, I have t squared minus 2t minus 3 is equal to 0. Now this is probably factorable. T squared will be t times t. 3 is 1 times 3. In order to get a middle of negative 2, I'm going to need a positive 1 and a negative 3. So it's factored. Using the zero product property, we set each of these factors equal to 0 in order to solve. So we know that we will have t is equal to negative 1 or t is equal to 3. They did say that we are supposed to use only times that are greater than or equal to 0. So we will disregard t equals negative 1. So that leaves t equals 3. So the answer is C. Number 6, given this equation, find dy dx in terms of x and y. So this is an implicit differentiation problem. So we will just take the derivative of each term with respect to x. The derivative of x to the third power is 3x squared. The next term, we are going to use the product rule. We have 3x and then we have y. So for the product rule, we take the derivative of the first factor, which will just be 3. And then we leave the second factor alone. But then we put a plus and we sort of go through it again. The second time, you leave the first factor alone. And you take the derivative of the second factor. The derivative of y is dy dx. So that's the product rule. Moving on to the third term, we're going to use the chain rule. So the derivative of the outer function is going to be 6y squared. However, because the inner function is not just x, it's a y, then the chain rule says we need to take the derivative of the inner function and multiply. So we will multiply by dy dx. And then we have the constant, and the derivative of a constant is 0. To solve this for dy dx, we need to get the terms that have a dy dx in it on the left side of the equation, and we need to put everything else on the right-hand side. So we will keep the 3x dy dx on the left side, and we will keep the 6y squared dy dx on the left side of the equation. But we will subtract 3x squared and 3y from both sides of the equation. So we will end up with negative 3x squared minus 3y. Now, on the left side of the equation, we will factor out dy dx as a GCF. So we will have dy dx, and that will leave behind 3x plus 6y squared. Now we will divide both sides by all of this. So that means this set of parentheses will end up in the denominator. So that gives us this. I'm noticing that every single term is divisible by 3. So I'm going to factor out a common factor of 3 from the numerator and the denominator. So that looks like this. But obviously, these 3's will now cancel each other out. So that will give us negative x squared minus y over x plus 2y squared. So this is what we are looking for. They're giving us one more little twist. They're putting the negative sign out in the front. Instead of having it distributed throughout the numerator, they have it out in the front. So let me go back and see if I can rewrite my answer. So I'm going to factor out -1 and put it in the front instead. So if I do that, I'm going to have this negative out in the front, and that will leave x squared plus y in the numerator. Okay, so now this is what we're looking for. So the matching answer is A. Number 7, last problem. Given this function, what is the value of the second derivative at the point 4, 3? Well, first we must find the first derivative by implicit differentiation. So let's take the derivative term by term. The derivative of x squared is 2x. Now, in the next term, because it is a y and not an x, get ready for the chain rule. For the outer function, the derivative is 2y, but then the derivative of the inner function is dy dx. The derivative of a constant is 0. Subtracting 2x from both sides, we have this. Now, dividing both sides by 2y, we have dy dx is equal to -2x over 2y. But these 2's cancel out. So really we have dy dx is equal to -x over y. In order to find the second derivative, we take the derivative of the first derivative. We're going to have to do the quotient rule, so you might notice that I moved that little negative sign from the front up into the numerator. That doesn't really change anything, but it makes it more clear what's happening with the quotient rule. Just in case you don't know the quotient rule poem, here it is. And where I say d, I mean the derivative of something. So it goes low d high, less high d low. Draw the line, and down below, the bottom squared will go. When I say low d high, low is the y value, and then d high is the derivative of the numerator, which will simply be -1. So that's low d high less high d low. High is just the -x. D low is the derivative of the denominator. So this is d low, dy dx. So this is low d high less high d low. Draw the line, and down below, the bottom squared will go. So there's your quotient rule. Simplifying a tiny bit, this -1, I just put the negative sign in the front, and minus a negative is addition, so there you go. Now I'm going to borrow from my previous work. We have this dy dx sitting here, but in the previous step we found that dy dx is -x over y. So I'm going to just make that substitution. So here I've done that substitution. On the next step, I'm going to multiply x times x, so I'm going to have x squared, and then this is plus a negative, which will just be a minus. So I could simplify this more, but ultimately we're to find what is the value of the second derivative at the point 4, 3. So at this stage, I could substitute 4 and 3 for x and y right now. So I think that's what I'm going to do. Just in case if I made a mistake simplifying, then that would throw off my answer. So maybe it will be safer to evaluate now. After the substitution of 4 and 3 for x and y, I get this. So now it's just a matter of simplifying. So far, I squared the 4 and got 16. I squared the 3 and got 9. On the next step, I will divide both of these terms by 9. For the fraction, if I divide by 9, that means the 9 goes in the denominator. So the denominator will be 27. So I have this, but I need like denominators. So I'm going to multiply by 3 in the numerator and denominator so that I have a like denominator of 27. So now I have like denominators, so I can go ahead and combine these into a single fraction with a denominator of 27. And in the numerator, I will have negative 25. This matches answer choice A.